Good day, everyone. And once again, we're back together. All right, so we're looking at question 6, which is momentum, work, energy, and power, right, from the IEB November 2022 exam. So if you haven't subscribed, please just make sure you're part of the family. And of course, we'll keep dishing out all of this good content. All right, so let's continue. They say to us, we've got a coin, which is a mass of 10 grams, which is pushed across a table with a frictional force, a constant force of 25 newtons. This force is applied at an angle of 15 degrees to the coin, right? They say, as shown in the diagram, so the coefficient of kinetic friction between the coin and the table is 0.6. Okay. Right, so firstly, they say draw a labeled free body diagram, right, showing the forces acting on the coin while it is being pushed. Right, so we're going to look at the free body diagram, right? So what are the forces that are going to be acting on the coin? Right, firstly, we know we will have the applied force, okay? So we can draw it over there. Right, we've got the force applied, right? And please, when they say label, please write out the words in full, okay? Otherwise, just provide, some descriptions for the acronyms if you use it. So the next force that we have is the gravitational force, or the weight of the coin, right? And in this case, remember, we also have the normal force, right? So the table exerts a force on the coin, right? So let me just try to make some space this side. Let me just write down the force that is applied onto this side. Force applied. And I said now I've got the normal force in this case, which is opposing, or that is going upwards. Okay, so that's the normal force. So those are the forces that are acting on that table, right? So they told us also about friction, right? So please note that because we've got frictional force, as we try to push the coin, now think about it, the horizontal equivalent of the applied force would be in that direction. So as a result, it means that friction will be in the opposite direction. So there we will have friction over there, right? So friction force. Okay, so those are the 4 forces that we've got, okay, that are acting on that object. Okay, right, so let's go on to the next question. They say to us, determine the magnitude of the vertical component of the force, right, that is applied to the coin. Now, firstly, what I want us to note, we've got a force that is acting in that direction, right? Right, so this is our applied force, and we know that it's acting at an angle of 15 degrees to the horizontal, okay? So we must now find, so it's acting at 15 degrees to the horizontal. Now, I want you to please note, so there will be 2 components in this case, and I want you to note very carefully. The first component will be the vertical component, which is going down, right? And the horizontal component, which is going in that direction now, which means the force applied in the y direction, the force applied in the x direction, or if you want, you can use parallel and perpendicular. In this case, we want the force that is acting in the x direction, which is the parallel force, right, to the motion, they said the magnitude of the vertical rather. So we're looking for FAY. Now remember, this angle here was given to us, right? They said to us, we are at an angle of 15 degrees to the horizontal. So that means this angle will be 15 degrees. Now you must remember that the horizontal and the vertical would make a 90-degree angle there. So I've kind of, created a triangle, right? So which side are we looking for? We are looking for the vertical component, which is FAY, right? Now, remember, we are given the applied force, that's 25 newtons. So we've got the hypotenuse, which is 25, right? So which trig ratio would say opposite? So that is directly in front of the angle. So that's the opposite side. And we've got the hypotenuse. So definitely that's going to be the sine of 15 degrees rather. Sine 15 is equal to FAY. Okay, over the force applied, FA, right? So because we're looking for FAY, we're going to say this is FA, the sine of 25. Okay, I'm just showing you how to go about that. So I'm just dragging it a bit. Okay, sorry, that's going to be 25 sine 15. I don't know why I keep saying sine 25. So that's sine of 15 degrees. All right, so let's calculate that. So that would give us 25, the sine of 15. Right, so that gives us 6.47. Now please note, this is how we would get the vertical component of the force that is applied. Okay, right, and then secondly, they say to us calculate the normal force. Now, right, guys, I want you to please remember this. So we're looking for the normal force. I want you to think about this. So we've got forces that are vertical, right? We would have, remember that FAY value is acting downwards, right? And we've got the weight of the object, okay, which is also acting downwards. And the only vertical force acting up is the normal force, right? So the normal force is acting against those two forces. And we know that this coin is not moving vertically, right? So in this case, it means that the sum of forces in the vertical direction will be equal to 0. And as a result, it means that the normal force will be equal to FAY plus, now remember these two are acting together, plus the weight of the object. So we already have FAY, which is 6.47, right? Plus the weight of the object, the mass of it is, they said the mass of the coin is 10 grams, right? So please remember, that's 10 grams, but we need to convert it to kilograms, right? So that's going to be 10 divided by 1,000, right? So this would be 0.01. So remember, when you've got mass in grams, you divide by 1,000 to convert it to kilograms, right? So the mass would be 0.01. Okay, so mass would be 10 divided by 1,000. Okay, and so that gives us 0.01 multiplied by 9.8, which is gravitational acceleration. Okay, so what would be the value of our normal force in that case? Okay, let's calculate it. That's 6.47 plus 0.01 times 9.8. Okay, So that gives me 6.57. All right, so that's the value of our normal force. Okay, right. Now they say to us, calculate the magnitude of... they said define normal force. I calculated the magnitude of the normal force. So this is what you would do in this next portion here. Okay, right. There you would write the definition of the normal force, right? It's a force that is perpendicular to the surface, right? In this case, that would be the normal force. All right, so 6.5, they say to us, calculate the magnitude of the frictional force acting on the coin as it slides, while it is sliding. Right, so remember they've given us the coefficient of friction, which was 0.6, right? And now we've got the normal force. So we can simply say, right, so friction would be the coefficient of kinetic friction multiplied by the normal force. So that would be 0.6 multiplied by 6.57. Right, you remember we got that value to be 6.57, which is the normal force, right? So I'm just going to multiply that value by 0.6 and I get 3.94, okay? So that would be 3.94 newtons. So that's the value of our frictional force. Right, now they say to us, determine the net force acting on the coin, right? So please remember, ladies and gents, we've got frictional force. We also have, now please note, when we looked at the force that is applied, we said it has two components. It has the vertical component, which was Fy, but it also has the horizontal component, right? No, actually that's in the opposite direction. So the vertical component would be downwards and the horizontal component is towards the right. Okay, so we knew this guy is 25 newtons, right? There was our angle, which was 15 degrees. And so, okay, in fact, I'm not sure why I'm even drawing this to be so small. Right, so you've got the vertical component, you've got the force that is applied, that was 25 newtons. So we want the horizontal component. Now, remember, the horizontal component, this should be 90 degrees, right? That's 15. So to get the horizontal component, which is the x part of the applied force, that's going to be on the adjacent side, and there's our hypotenuse. So to get FAX, we're simply going to have, in fact, let's write it out in full, which means the cos of 15 is going to be adjacent, which is FAX, over hypotenuse, which is 25. So which means FAX is equal to 25 cos 15. Right. Now, ladies and gents, I'm not going to work it out at the moment. So this is the value of our component of the force. So horizontally, which are the forces that are acting? It would be FAX, but you agree with me, it would be opposed by the frictional force, right? So therefore, F net would be equal to FAX minus the frictional force, kinetic friction. So that would be 25 cos 15 minus the frictional force was given as 3.94. I hope I'm correct, right? So 25, the cos of 15, okay, minus 3.94. Okay, Right, I get a value of 20.21 newtons. All right, so that's the value of our net force in this case. Right, next question. They say state the work energy theorem. Okay, remember, we simply say that the net work done on an object is equal to the change in its kinetic energy, right? So the net work done on an object would be equal to the change in kinetic energy, right? So the next question, they say calculate the gain in kinetic energy of the coin, right, as it is pushed with a steady force over a distance of 20 centimeters, right? So what are we going to do? We're looking for the change in kinetic energy. But remember, we said that the net work done is that change in kinetic energy, right? So I'm going to find out what the net work done is. I already have the net force multiplied by delta x, the cos of angle theta, right? So my net force, the value of my net force was 20.21, okay? So this would be 20.21. My displacement is 20 centimeters. Now remember, when we've got centi, we divide by 100 cent, and 100, just like percent. All right, that's over 100. So in this case, that's going to be 20 divided by 100, and that would give me 0.2. So the displacement is 0.2. the cos of. Now, please, I want you guys to note, as I've taught in the past, the angle theta would always be the angle between direction of motion and the force in question, right? In this case, we're talking about the net force. We found it to be positive, so which means it's in the direction of our motion, right? And in this case, the displacement is also in the same direction, so that will be cos of 0, right? The angle between those will be 0. Right, so let's quickly have a look at it. So that's 20.21 multiplied by 0.2, okay? And so that gives us 4.04 newtons, okay? So that would, sorry, not newtons, rather, joules. So this would be the gain in kinetic energy. Remember that the net work done is equal to the change, or in this particular case, the gain in kinetic energy. Okay, right. The next question, right, they say how much energy is used to overcome friction as the coin is pushed over this 20 centimeter distance, right? So we want the work done to overcome friction. So this would be the frictional force multiplied by delta x, again, the cos of angle theta, right? So you've got the frictional force, believe it was 3.9, where was that value? 3.94, right? So that's 3.94 times delta x, the 20 centimeters, so that would be 0.2, the cosine of. Now remember that the direction of motion is to the right, but friction is opposing that motion. So what would be the angle between the two? That should be 180. Okay, right. So I'm going to say 3.94 times 0.2, okay? Cos of 180, remember that makes it negative, right? Sorry, that's cos of 180. Okay, so I get a value of negative 0.79. And again, this is joules. So remember, the work done by friction would be negative because we are losing energy, right? Because of friction, right? So as a result, the work done there would come out as negative. Okay, that's energy lost to the system. All right, ladies and gents, that is how the cookie crumbles when it comes to this question. I really hope that you were able to follow and understand. All right, so we'll be looking at the next section. Please look out for more. Otherwise, from me for now, I'll see you guys again next time. Sharp, sharp.